Welcome back. This is the day the Lord's made. Let us rejoice and be glad in it. In this video, I'm going to talk about two things. First, I'm going to talk about the solubility table and talk about solubility in general. Second, I'm going to talk about electrolytes. So first off, the solubility chart. So a solubility chart just basically tells you whether something will dissolve into a solution. The solubility chart we're looking at here will be for water only. And we're talking about neutral water too, because if you change the pH, you change whether some things are soluble or not. So the chart that we're looking at here, the one we use in our class, we have the rules found on the left side. So anything on the left side is the rule. And if there's an exception to the rule, it's on the right side. And so we should remember too, the word soluble means that it will dissolve into it. Like sugar dissolves into water. So sugar is soluble in water. If we say the word insoluble means does not dissolve. So like your skin is insoluble in water for the most part. So, all right, so we should also mention too, these rules, the exceptions are to the right, and they're just, these go together. So rule 1's here, and its exceptions to the right. This exception here is only for rule 1. It does not apply to the other rules here. So if I'm looking at rule number 3, the exceptions are found directly to the right here. These exceptions do not apply to other ones. So what does this rule say then? This rule says all nitrate, nitrite, chlorate, perchlorate salts are soluble. What that means is if you take these polyatomics and mix them with any metal, so gold nitrate, silver nitrate, iron nitrate, sodium perchlorate, any one of these things, you put them into water, you take that salt, put it into water, it will dissolve. This chart does not tell you the limit of its saturation, meaning like how soluble is soluble, like how much can we put in it. It's just a general rule. It says it will dissolve. You'll be able to dissolve something into it, okay? Also, when you're looking at this chart, even though the rules should not contradict, you should take the first rule to be the most important in the deck. And as you go down, they're less important. But again, these rules here, rule number 1 will trump rule number 2, but they never should disagree. So hopefully, unless I made a mistake or have a fault in here. So anyway, so again, nitrates, those guys are soluble. All the alkali metals and ammonium are soluble. Again, you might see the pattern here too. General rule, +1, -1, those things tend to be soluble in water, all right? So there are some exceptions for the alkali metals. There are some lithiums that are insoluble. More on that later. Usually halogens are soluble. So anything with chloride, bromide, iodide, those things will dissolve into water. Again, we have a big list of exceptions. These exceptions then, if you have an exception, you don't follow the rule. So if we have NaCl, sodium chloride, Cl, the rule says soluble. Is Na an exception? Na is not an exception, so we follow the rule. But if we have an exception, we don't follow the rule. So if it was silver chloride, AgCl, would silver chloride dissolve? Cl normally dissolves, but in the presence of silver, it does not dissolve. So it'd be insoluble. So if there is an exception, you don't follow the rule, you do the opposite. So acetate generally dissolves with almost everything. There's only a couple exceptions where it will not dissolve. So silver acetate, mercury acetate, those things would not dissolve. Sulfates tend to be soluble. This has a bigger list of exceptions. Sulfides tend to be insoluble, again, with these exceptions. So, again, we should remember that the rules are on the left, exceptions on the right. The rules should not disagree, but if you're comparing them, the rules higher up are more important, all right? And if you're not sure, if you can't find something, if it's a big charge, like and by big charge, I mean -2, +2, -3, +3, those things tend to be insoluble. If it's some compound that's not on here and it has a charge that's not ± 1, you should consider it to be insoluble in water. So also we should talk about double displacement reactions and whether they make a solid or not. If you mix things together, do they make a solid? So if you're to mix sodium hydroxide, and if sodium hydroxide, this is something that's soluble. So rule number 2 says Na is soluble. So Na is soluble. OH is not an exception. Magnesium chloride. Rule number 3 says chlorine is soluble. However, if we mix these things together inside of the solution, then if we had the resulting solution with both these coming together, then the OH would run across the magnesium. And then because of rule number 8, normally hydroxide salts don't dissolve, they're insoluble. Magnesium is no exception, so we would find out that magnesium would actually react with magnesium or with the hydroxide to make a solid. So for these things here, if I ever ask you a question like, will these two things when mixed together make a solid, you're going to do a double displacement reaction, because the first thing listed is always going to be positive. So first thing listed is positive. First thing listed is positive. Those are the cations. They're not going to come together. All right. What's going to happen is we're going to take the negative from the first one, and it's going to try to react with the one on the back side. So we're going to do a double displacement reaction. Will the Na and the Cl make a solid? Will the Mg and the OH make a solid? Because positives do not react with positives, and negatives do not react with negatives. So the only possibility for something becoming insoluble is a positive and negative to like each other enough to not hang out the water. So anyway, KNO3, this thing would dissolve with anything. There's no way to get it out of solution through a precipitation reaction. So if you were trying to get rid of the nitrates in the water, you can't use a precipitation reaction to get rid of it. So if you're working for the water treatment center, nitrates are hard you can't get them out of the water through a precipitation reaction. We could get rid of silver out of the water or lead out of the water easily. So like if we look up here, if our water is contaminated with silver, or if it's contaminated with copper or lead, how can we get it out of the water? We would just put a little bit of table salt into the water. If you pour some table salt into the water, then the Cl would react with any one of these guys to make a solid, which would take those things out of the water. So you can think about water treatment center, a way that they get rid of chemical pollutants is they can just basically mix elements together that like each other to make a solid, and then it's no longer part of the solution. It'll come out. So we'll just real quick do a couple together as examples, and then we'll move on to electrolytes. So do we expect CaCO3 to be soluble? So we're going to find some rule that talks about one of these guys here. The first time we run across CaO3 is down here. So carbonates tend to be what? Slightly soluble. And for the scope of this course, if it says slightly soluble, you're going to consider that to be insoluble, because slightly soluble means hardly any dissolves, like a little bit, which means that kind of like when you take a shower, like your skin, even though we say it's insoluble, you might lose a couple cells. All right, your skin is slightly soluble. All right, we're going to consider slightly soluble to be insoluble for the scope of this course. So carbonates tend to be insoluble. Is calcium an exception? No. Therefore, we're going to say this one is insoluble. Would AgBr, would this dissolve into water? If we took AgBr, put it into water as a salt, would it dissolve or would it stay a solid? Rule number 3 says Br tends to dissolve. However, silver is an exception. So what does that mean? We're going to not follow the rule. We're going to say that's insoluble. Na2SO4, sodium sulfate. Rule number 2 says that Na is soluble. Is sulfate an exception? No, this is soluble. It would dissolve. LiCl, Li, alkali metal. Cl is not listed as an exception. This is going to be soluble. Magnesium hydroxide. Hydroxide is found down here. They tend to not dissolve. They tend to be insoluble. Magnesium is not an exception, so we're going to follow the rule. So that would be insoluble. Iron nitrate, iron 2 nitrate. Nitrate is always soluble. There are no exceptions. Ammonium nitrate. Ammonium and nitrate are both soluble, although we just need to know one of them. So this should be soluble. Rule number 1 says nitrates always dissolve. Cesium, that's an alkali metal. Therefore, this will be soluble. We should mention too that makes a difference how big you are. Again, this is just going a little further, like discussing the general trend. The size ions make a big difference in whether you're dissolved or not too. So for example, lithium has some exceptions. The reason for that is because lithium, compared to the other alkali metals, is super tiny, which means its positive charge is really condensed, which makes them super sticky, which means that if there's some negative nearby, it would really like it and it would stick to it and not let go. Therefore, it wouldn't dissolve. So, and we can see this in the alkali earth metals, you know, the general idea is barium and calcium for rule number 8, they're exceptions. So if we look up here, rule number 8 says these guys tend to be insoluble, but barium, strontium, calcium, These guys here, those three right there, they're on the bottom of the alkaline earth metal section. So you're going to atomic trends, as you go down the periodic table, you get bigger. And so down there, these atoms are really big, which means that that positive charge is spread out really thin. Because that charge is spread out thin, it's not very attractive, and therefore the hydroxide says, I'm not quite as attracted to you, so we can part ways. All right. But at the top of the chart, the alkaline earth metals, we have beryllium, magnesium. Those things are tiny, which means their +2 charge is larger, which makes it more attractive to the OH, and it won't let go. So again, magnesium, beryllium being tinier, their atomic radius is smaller, that positive charge is more compact, and it's going to be much more attractive. So again, these rules up here basically are just atomic trends and these forces of attraction between positive and negatives. In general, as the positive atoms get tinier and tinier and tinier, they get more insoluble because they get stickier. So that's also too why this chart doesn't include fluorine on here. Again, fluorine, he's very tiny and even though he has the same negative charge as chlorine, bromine, and iodine, he's just extra sticky. So, all right, switching gears here then. This is connected to solubility. This is our B-level topic. It's about electrolytes. So an electrolyte just refers to charged particles in solution. Are there ions in the solution? Because if there's ions in the solution, it helps carry a current, helps carry electricity. Again, our body uses electrical signals. It primarily uses like sodium and potassium and chlorine for doing its work. You know, it also uses other ions too, like magnesium. There is even some gold ions that get used, especially in the heart area. But general idea is an electrolyte, when someone says it, an electrolyte just means an electron carrying particle inside the solution. You know, you can go buy a bunch of these in Gatorade. You know, although we should mention that, you know, Gatorade is just basically water with a lot of sugar and a pinch of salt. If you take a pinch of salt and put it into water, you got electrolytes. All right, you drink that down, you'll get some electrolytes. So in this class, we're talking about whether you're a strong electrolyte, a weak electrolyte, or a non-electrolyte. So if you're a strong electrolyte, this means that you are really good at conducting charge. You make the solution very conductive. All right, so these would be things that would be salts or strong acids and strong bases. All right, those things fully ionize. So if you think about a strong acid, the definition of a strong acid is that it fully ionizes. So something that fully ionizes turns into ions. And so you're gonna have a whole lot of ions, which means it's great to conduct electricity. Now, all salts also count for strong electrolytes as well, because even though there's not much that actually dissolves, there's enough that it does make it conductive. All right, or I should say that they are, the ions that do show up are very conductive. All right, so in this class here, we're going to say that if you are a strong electrolyte, if you're a strong acid or a strong base, or if you're a salt, because the salt will break into ions, it will ionize at least to some extent. All right, you will be a weak electrolyte if you are a weak acid or a weak base. All right, so weak acid, weak bases, those things are weak electrolytes. So a weak electrolyte is weak because there's a couple of ions in the water, not a lot. All right, very small amount of them, which makes it just slightly conductive. And you're a non-electrolyte if nothing ionizes, if you have no ions in the solution. So like when you put sugar in the water, the sugar does not ionize. The carbons and the hydrogen and oxygens all stick together, nobody lets go, no one becomes ionized. The molecule, even though it's changed in the water, it's not an ion, so it doesn't carry an electricity. So you're a strong electrolyte if you're a strong acid, strong base, or if you're a salt. You're a weak electrolyte if you're a weak acid or weak base. So you can ask yourself these questions too. Is it a strong acid? All right, because if it's a strong acid, then it is going to be a strong electrolyte. Again, in case you've forgotten them, we can mark them down again. HCl, HBr, HI. Those guys are the halogen ones. Then we have sulfuric acid. Then we have perchloric acid. And then we have nitric acid. Those things right there, those are the strong acids. This class, got this here, it says 7. Sometimes people consider like chloric acid to be strong as well. So what are the strong bases? Strong bases are any alkali metal with an OH. So NaOH, CsOH. There might be some other strong bases out there as well, but I don't think on the scope of this course I used them ever. All right, but in this class here, strong bases, if you have a metal with an OH, we're going to call that strong base. They're not all strong bases, but they're at least strong electrolytes. All right. Is it a metal with some non-metal? Is it a salt? Yes, those things are strong electrolytes. You can figure that out. Does it start with an H? Again, in general, we put an H on the front of anything that when you want to communicate to people that it is a weak acid. So like HC2, H3, O2. Why do we put the H on the front? Why is there an H right there? The H on the front is separated from the other hydrogens because we're trying to tell you something. We're saying it's a weak acid. That is an acidic hydrogen. It will ionize to some extent. All right. If it has a nitrogen with hydrogens on it, it might be a weak base. But as far as this class goes, you can just assume if it's not a strong base and I tell you it's a base, it's a weak base. So, and if it doesn't fit any of those criteria, we're going to make it a non-electrolyte. So, all right, God's peace.